Welcome. So the topic we will be discussing in this lecture is micro-programmed control. So basically we are discussing how the CPU will generate the control signals to execute a given instruction. For a given instruction in assembly language, the instruction may be actually it may be divided into several small steps and appropriate control signals has to be generated so that that instruction can be executed successfully. So there are two ways to generate such control signals. The first method is by using hardwired control, which we have discussed in the last lecture. The second method is by using micro-programmed control. So that is what we are going to discuss in this particular lecture. Okay. So hardwired control actually it would be very fast, but it is not flexible because every control signals should be generated by providing appropriate hardware connectivity, okay, which may not be always possible. Right? So, so there is another method to generate these control signals, that is by using micro instructions. That is by using micro instructions. So how it is being done? That's what we are going to discuss in this particular lecture. Right? Okay. So before starting the actual concept, we will first discuss certain terminologies that were connected with this microprogram control. So first thing we'll be using something called as control word. So what is a control word? In the sense, a control word is a sequence of memory locations. It is a sequence of location. Memory in the sense this memory is a part of CPU. Okay. So control word is something it represents some sequence of bits. Okay. You can say it is a sequence of bits where each bit will represent one instruction. Each bit will represent one instruction. Maybe this bit may represent PC out. Okay, it means whatever is in PC that should be moved to the internal bus. Okay, this is PC out. This may represent this next bit may represent read. It means whatever the address that is specified in MA or in MA or memory address register, that content I want to read. Okay, maybe another one may be MDR out. So whatever in MDR memory data register, it will be sent to the internal bus. Like that, each bit will represent one instruction. Okay. So what are the possible instructions for everything? There will be one bit. Okay? So if you want to execute this instruction, then this bit should be set one. If you want to execute some other instruction, then that bit should be set one. Okay. So this is called as a control word. A control word is something. It is a it is something like a collection of bits where each bit represents where each bit represents a particular micro instruction. Okay, fine. So a sequence of control word. A sequence of control word is called as micro routine. A sequence of control word is called as micro routine. If you want to execute any instruction, say for example, if you want to execute this instruction, add R1 comma R2, which will add R1 and R2 and store the result in R2. Okay, this may be converted into several small steps. Step one, something to be done. Step two, should be done. Step three, something should be done. And this should be done in some sequence. This should be done in some sequence. Okay. So each of this sequence will be represented by control word. First sequence will be represented by control word in one order. Okay, I mean different combination of zeros and ones. Zero means we are not executing that particular instruction. In that bit position, if it is zero, then we are not going to execute that instruction during that time. Okay, during second step, some other combination of zeros ones will be there. So wherever one, that instruction will be executed. During third step, there will be some other combination of zeros and ones. Okay, so this actually it is not that it can be in any order. It actually follows some particular order or sequence. Okay? So this sequence of control word to execute a particular assembly language instruction is called as micro routine. It's called as micro routine. Okay, fine. And out of these individual control words are called as micro instructions. So this is one control word. Okay, so this is one control word which is a combination of zeros and ones, which says actually what instruction to be executed. So this one control word is called as one micro instruction. This is another micro instruction. This is another micro instructions. All these put together, maybe not only four, three steps, it may be 4 or 7 steps, whatever it may be. All these put together is called as micro routine. It is called as micro routine. Okay. Okay. So these terminologies we'll be using here: control word, micro routine, and micro instructions. Okay. Control word is nothing but the representation of instructions. Each micro instruction is represented by using some bits. Okay, and if the bit is 1, it means we are going to execute that instruction at a given time. If it is 0, it means we are not going to execute that instruction. Okay. Now let us understand this with an example. Right? So here, so in the last lecture we have discussed that this particular sequence. Okay, this is actually to perform this particular operation, add R3 comma R1. This we have discussed in the last before lecture or somewhere. Right? So it is supposed to add the content of R1 with the with the with the content represented by the memory location specified by R3. Okay. So R3 is actually referring to some memory location. So if R3 is equal to 2000, it means that R3 refers to the memory location 2000. And in this memory location 2000, there may be some value, say 15. Okay, and if R1 is 20, it says that these two things should be added. 20 should be added with the 15, and the result will go to R1. Okay, so this R1 will have 35. Okay, so this is what is expected to be done. So this, if you want to do this using a single bus architecture, then this will be the number of steps required. Totally we need 7 steps. Okay, each step corresponds to one clock cycle. During first clock cycle this will be done, during second this will be done, during third this will be done, so on and so forth up to the 7th clock cycle. So these instructions already we have discussed several times. I think we should be clear with this. Okay, now what we are going to discuss is how these instructions will be, these steps, how it will be executed, actually how it will be done, how the appropriate control signals will be generated by using microprogrammed control. Okay, so you refer this particular diagram. Here we maintain something called as control word. That is, the CPU maintains something called as control word. Okay, so control word is a sequence of bits. Okay, so where each bit represents one micro instruction. You can see here the each column represents one micro instruction. First column represents PC in, next represents PC out, next MAR in, read, MDR out, IR in, Y in, select. So select means it represents actually select 4. Okay? So if it is 1, it will select 4. If it is 0, then it will select Y. Okay, you recall that diagram of ALU in a single bus architecture. Okay, in ALU, if this is the ALU, okay, then there is something called as uh, uh, there is something called as multiplexer. Okay, so there is a multiplexer. One of the multiplexer input is coming directly from Y, the other one is will be from 4. Okay, any one will go here. If 4 is selected, this will go, otherwise Y will go. This will be, the other input is connected to the system bus. Okay, right, I mean the internal bus. Okay? So select 4 is select 4 is one of the instruction, add is one of the instruction. Like that, all the possible instructions were included here. Okay, so it's not that only this many instruction. It goes on, the list goes on. Okay, but for executing this particular instruction, this particular assembly language instructions, this instructions is sufficient. So only that much is shown. Okay, now you see this is at step 1. At step 1, which instruction should be executed? PC out, MAR in, read, select 4, add, Z in. So only those are enabled. PC out is enabled, MAR in is enabled, okay, read is enabled, select 4 is enabled, add is enabled, zin is enabled. Okay, so all these, whatever the steps required at step 1, all those were enabled. Okay, so it means that at step 1, the processor, step 1 means during the first clock cycle, processor will generate these signals in this order. First it will generate this signal, then this, then this, then this, then this, then this, but everything will be done in first clock cycle itself. Right? Similarly, during the second clock cycle, only these signals are enabled. You can see the rest are zero. What are they? PC in, Y in, Z out, and WMFC. So you can see the second instruction, it is Z out, PC in, Y in, and WMFC. Okay, right? So similarly, in the third clock cycle, MDR out and IR in. Only those two things are enabled, MDR out and IR in. Okay. Similarly, in fourth step, R3 out, MAR in, and read. R3 MAR in, read, okay, and R3 out. Okay, all these are done in one clock cycle, so it can be of any order. That's not an issue. Okay, so within this clock cycle, it can be of any order. But before this particular thing is done, the previous clock cycle micro instruction should be completed. Okay, so this is how basically the control signals were generated by using microprogrammed control. Right? Okay. So this is a very basic example like how the concept of microprogrammed control works. Right? Okay. Now, for this particular, if you want the processor to work in this style by using microprogrammed control, then the processor organization should be slightly modified. Okay, the processor should include something called as control store. The processor should include something called as control store. So you may ask, what is control store? Control store is something like a memory. Okay, control store is something like a memory, and this memory is placed inside the processor. Control store is a memory which is placed inside the processor. And what this memory will contain? Control store is a memory, and this memory is placed inside the processor. And what this memory will contain? This memory will contain all the micro instructions. See, these are the micro instructions. Okay, all these micro instructions will be stored in the control store. All these micro instructions will be stored in the control store. Okay, so micro instruction, say for example, this particular processor, it supports 100 micro instructions, then all the micro instructions will be stored in this control store. Micro instruction 1, micro instruction 2, up to micro instruction 100, all the control instructions will be stored here. Okay, and like how in the PC, in the in the processor, we have program counter, which always points to the address of the next instruction to be executed. It points to which address? It points to the address of the memory, main memory. Okay, but main memory is outside the CPU. Main memory is outside the CPU. Okay, this is CPU. This is CPU. So if you want to perform microprogram control, first thing you should have control store. This is control store. I'm calling it a CS. One more unit we have, which is called as micro PC. This unit is called as micro PC, which is called micro program control. This is called as micro program control. Okay, because PC will load the instruction to the instruction register IR. Okay, PC will, the address in the PC will first go to MAR, and from there it will, and MAR will give the read operation, and the instruction will come to MDR. Okay, and from MDR it will come to IR. Okay, MDR it will come to IR. Okay, fine. From IR, but IR, again from IR, if you see the for example, if the instruction is maybe in assembly language, the instruction may be something like very simple instruction like R1 comma R2, add R1 comma R2. It is add R1 and R2 and store the result in R2. But when you convert it to uh, when you want to generate the respective control signals, this itself may take some 5 or 6 steps. Okay, like how in the previous case we have discussed. So it cannot be done in one clock cycle. It may take at least 4 or 5 clock cycles. Okay, so again this will be divided into several small micro instructions. Okay, those So that may refer to one of the micro instruction, each of the micro instructions in the control store. Okay, and at different steps it may refer to different micro instruction. Are you getting? At step one, it may refer to some one or two micro instructions. At step two, it may refer to some other micro instructions. At step three, it may refer to some other set of micro instructions, where each step represents one clock cycle. Okay, so so this is also a memory. So at each step, which memory location should be accessed and which instruction should be executed, that should be known. Okay, how to know that? That will be generated by micro PC. That will be generated by micro PC. So micro PC will generate the appropriate address of the control store, like which micro instruction should be executed. Okay, so each micro instruction will be stored in some part of the memory. Okay, so if at a particular time, if the micro instruction X is to be executed, uh, micro instruction X, which is stored at address say 2000 to be executed, then it will generate the address 2000. So that instruction will execute. Okay, so so the processor organization should be modified in this way. Okay, so from IR, so instruction register is the one which contains the instruction. Okay, so from IR, the starting address generator will generate the starting address of the micro instruction. Okay, because IR contains that assembly language instruction, but when you convert it to a micro instruction, uh, it may have several micro instructions. In each step, there may be some set of micro instructions. Okay, so which micro instruction should be executed first? That starting address will be generated. Okay, and micro instructions, where it is stored? It is stored in the control store. Okay, and that starting address will be first generated by the starting address generator, and from there it will go to micro PC. Okay, so micro PC, what it will do during the first clock cycle, whatever the whatever the instructions which are referred by the starting address, only those instructions will be enabled. Okay, and then that is the control word generated. Okay, that is the control word. Control store contains all instructions. Okay, now whatever the address created by micro PC, and that address refers to which instruction, only that instruction will be fired. Okay, or or or, or the control signal corresponding to that instruction will be enabled. Okay, then then accordingly, the arithmetic logic unit or control unit will perform the operation. Okay, then when the next clock cycle comes, during the next clock cycle, the micro PC will be updated. Okay, it will be incremented, and the next instruction will execute. Okay, again during the next clock cycle, again it will increment. Like that, all the micro instruction will execute. Okay, so if you see here, this contains 7 steps. Okay, so in that case, it means that this set of micro instructions will be available in one location in the control store. So if it is available in 1000, then the starting address generated will be 1000. So that will execute first. Okay, then this will execute. Whatever next, say let us assume 1001, this will execute. Then 1002, this will execute. Like that, after executing every instruction, the control store, the micro PC will update, and the appropriate instruction will execute. Okay? So you should remember one thing: micro PC refers to the address of control store. Okay, it does not refer to the address of main memory. Whereas PC, program counter, refers to the address of the main memory. Okay, fine. So this is how actually micro-programmed instructions, or control signals, are generated by using micro-programmed control. Okay. Mm. But this particular organization, it cannot carry one one particular operation or one particular function. What is that function? In the sense, if you want to perform a branch instruction, that logic is not included in this organization. Okay, so if you want to perform a branch instruction, then how it should be done? So this particular model or organization should be slightly modified, something like this. Okay, then you can perform the branch instruction. That is, so all these parts are same as that of the previous diagram. So in the previous diagram, you have this entire thing. To this, we are adding whatever the output of the control store generates some signals. Okay, that we are checking. Okay, whether by we are comparing with something here that is not shown. Okay, we are comparing with something like whether we may check whether with some control flag, whether zero flag is set or not, whether negative flag is set or not, whether overflow flag is set or not. Okay, if any one of these flag is set or reset, then instead of following the normal flow, the program may have to execute some other instruction. Okay, so such cases we call it as branch instruction. Okay? But this is called as conditional branch. This is called as conditional branch. Okay, unconditional branch is not specified here. This is an example for a conditional branch. That is, if any one of these flag or if any external input were enabled, that will be checked whether it is enabled or not before generating the control word. If it is enabled, then the normal flow of the program should be changed. So once again, what will happen in the sense, the control will go here, and the starting address generator or the branch address generator will generate some other address, and that address will go into micro PC. Okay. Now micro PC may refer to some other address in control store, and that instruction will execute. Okay. So this is how branch instructions are handled by using microprogram control. So here is an example which shows how it works. See, this is the first step is nothing but uh, up to this is nothing but instruction fetch. Okay, this is as usual whatever we are discussing in the previous case. All these first three things are nothing but instruction fetch. Not only instruction fetch, and also we are updating the PC to the next address. Program counter is updated to the next address. Okay, right? Then branch to the starting address of the appropriate micro routine. Then there is a branch instruction. Okay, then there is a branch instruction. This is actually this instruction 3. It refers to unconditional branch. It refers to unconditional branch. That is, the instruction itself is a branch instruction, so it will go. Okay, but after that there are some instruction 4 to 24. We are not bothered of that. 25th is a conditional branch. 25th is a conditional branch. After performing some operations, maybe some addition or subtraction, multiplication is carried out before 25th step. At 25th step, we are checking whether n is equal to 0 or not. N is negative flag. Whether negative flag is set or not, we are checking. If it is 0, that is, if it is not set, then what we are saying that branch to micro instruction 0. What is micro instruction 0? This is micro instruction 0. It is once again you fetch the next instruction. Once again, micro instruction 0 means this will execute. What is this? What is this? Whatever in PC will come and read that. That means basically it is saying fetch the next instruction and execute the next instruction. Okay. Under which condition? If n is 0. So if n is 0, then it means that the control is moving to the next instruction. Okay. But if n is 1, if n is not 0, then this will execute. Okay. What is this? Take the offset part from IR. Currently, whatever is in IR, from that take the offset and add with and add that with y. Okay, select y, add that with offset. What is y will be having? If you recall, y will be always having whatever PC is having. Okay, PC, if PC contains the address of the next instruction to be executed, so say PC contains 2004. Okay, then y will also have 2004. Okay, because here you can see Z out, PC in, and Y in. That is, Z out is nothing but the address of the next instruction. Okay, that comes to PC in, and also that comes to Y in. Okay, that comes to PC in, and also that comes to Y in. Okay, so here select 4 is what 4 we are selecting, and add is what add with the current content of Y. Current content of Y is the older content of Y, that is 2000. Okay, that is the, say let us assume 2000 is the first instruction. Then 2000 plus 4 is 2004. That we are sending to PC and also to Y. Okay, right? So here offset field of IR means, in the last class we have discussed how we will identify the offset. For getting the offset, you have to find the difference between the PC and the target address. So if the target address is 2050, okay, then the offset will be 2050 minus PC content. PC content is 2004. Okay, it is actually difference. 2050 minus 4 is 46. Okay, that 46 again you add with PC. So if you add, what you get? If you add this and this to 46, you get 2050. Okay, so this 2050 is nothing but the target address. This 2050 is nothing but the target address. Okay, so so it says go to that target address. Okay, if I mean, if n is 0, then it will go to the next instruction, otherwise this will happen. Okay, that is offset will be moved to offset, and 2004 will be added. Okay, and that will go to z in. Okay, and from z that goes to PC. So now PC becomes what? 2050. So it means the control has transferred to the branch location. Okay, right? So so how this can be implemented using a micro program? The control means it is like this. Okay, so the control store checks. Here it will check what is the uh, uh, yeah. Here it will check for the condition codes. Here the condition codes are there, right? So based on the condition codes, the appropriate what do you call, the appropriate if the appropriate flags were set, then some other address will generate and that address will come here. Okay. If it is unconditional branch, then there will not be any checking. Directly that address will be created and that will come into micro PC. Okay. So this is how the micro program, the control concept works. So let us stop here. Thank you.